In this video, we will be discussing about the Gauss Seidel method for solving systems of equations. The Gauss elimination method as well as Gauss-Jordan method used for solving systems of linear equations. But if we apply Gauss Seidel method, we can solve systems of any type of equation, whether it can be a linear equation or it can be non-linear equations. The only condition is that each of the variable should be expressed as a function of all the other variables and constants. This presentation goes through a short introduction into the iterative methods, and then it describes about the Gauss Seidel iterative method. Then an example is solved using the Gauss Seidel method, and finally a summary. In the case of Gauss Seidel method, it is an iterative method. An iterative procedure means it goes through different iterations in which the solutions are bettered. That is, better solutions are found out during each iterations. In the case of the other methods like our elimination methods like Gauss elimination method or Gauss-Jordan method, they are direct methods in which we find out the values of the variables directly. But in this case, in each of the steps we will be having a set of values which are probable solutions. But this set of values will be having some errors, and in each of the iterations we are reducing the amount of error present in that particular set of values. So, an iterative method for solving a system of equation is in which we start from an approximation to the true solution. The approximation can be all the values equal to 0 or all the values equal to some particular specific values, something like that. Depending on the conditions that we have, we select the initial solutions. Then, if successful, we obtain better and better approximations from a computational cycle which is repeated as often as may be necessary for achieving the required accuracy. The number of iterations or the number of computational cycles varies from the point of view of the accuracy. If we require a more accurate solution, then the number of cycles will be more or the number of iterations will be more. And if we require only a less accurate solution, then the number of iterations can be less. And the condition for applying this method, the iterative procedure, is that we will be successful in representing each of the variable as a function of the other variables. We go for the iterative methods if the convergence is rapid. That is, if the matrices have large main diagonal entries, if we represent the coefficient of the variables as a coefficient matrix, if the main diagonal has large entries compared to the other entries, then we can go for the iterative methods. If the main diagonal entries doesn't contain the largest elements, then it is better to go for the direct methods. Again, we can use the iterative methods if a large system is sparse, that is, it has many zero coefficients, so that one would waste space in storing zeros. Like, suppose we have a system of equations in which there are 20 variables, and in each of the equations there are only some say 3 to 4 variables are present, and the coefficients of all other variables will be 0 in that case. So, in that case, we can go for the iterative methods, since if we represent the coefficient matrix, many of the spaces will be occupied by zeros, and it has no use in that case also. And if we go for the direct methods, there will be waste of space for storing all these zeros. Now, let's go to Gauss Seidel iterative procedure. Actually, this is a technique for solving systems of linear equations of any size Obviously, as I said earlier, it can be used for systems of non-linear equations also. The only condition is that we should be able to represent the variables as a function of the other variables. And the steps of the Gauss Seidel methods are followed. The first step is we have to express each variable as a function of the other variables and constants. And then we assume zeros, or it is possible that we can assume other values also for all variables except the first one. Now we calculate the value of the first variable using the function for that particular variable and substituting the assumed values for all other variables. Then we calculate the value of the second variable using the calculated value of the first variable and assumed values of all other variables. Then we repeat the steps for all other variables, and while calculating the value of a variable we use the latest value for all other variables. Now once the initial values of the all variables are computed other than the assumed values, then we say that one iteration is complete, and then we go for multiple iterations, or we repeat the iterations until the desired accuracy for the values are obtained. So now through an example we can explain the steps again. So in order to explain the steps we use this particular question, that is, solve the following system of equations: 8x minus 3y plus 2z equal to 20, 4x plus 11y minus z equal to 33, 6x plus 3y plus 12z equal to 36. If we create the augmented matrix, the main diagonal will be having the elements 8, 11 and 12. The augmented matrix in this case will be 8 minus 3, 2, then the vertical line 20, then 4, 11 minus 1, 33, 6, 3, 12, 36. So this is the augmented matrix, and the main diagonal in this case is this diagonal. See, the largest elements in the coefficient matrix lies in the main diagonal. So in this case it is better to use an iterative procedure for solving this system of equations. Now, as we said earlier, the first step in solving this system of equations using Gauss Seidel method is we have to write the equations in the form such that the left hand side consists only the variable and the right hand side consists of a function of all other variables and constants. In this case we can write this equation, or we can write the first equation as x equal to 1 by 8, 20 plus 3y minus 2z. And the second equation can be written as y equal to 1 by 11, 33 minus 4x plus z. And the third equation z equal to 1 by 12, 36 minus 6x minus 3y. Since we are going for a system of linear equations, it is easy to express the variables in terms of the other variables. When we go for some non-linear equations, still we have to express each variable as a function of the other variables. Now the equations are represented as the top line. Now we assume the values of x, y and z as x0 equal to 0, y0 equal to 0 and z0 as 0. And here we represent the variables as well as the values of the variables during each iteration in a table. These are the variables, and in the iteration number is given here, and the corresponding values of x, y and z during that particular iteration is given here. So during the 0th iteration, that is the assumed values are zeros, 0 and 0. Now we substitute the value of y and z in the equation for x and find out the value of x. This is the first step in the first iteration. So the equation for x is x equal to 1 by 8 into 20 plus 3y minus 2z for the first iteration. So in order to find out the value of x1, we have to replace the value of y with y0 and value of z with z0. Here y0 is 0 and z0 is 0. So we obtain x1 as 2.5. So that particular value is inserted here. It is during the iteration 1, the value of x is 2.5. Now in the next step, that is the second step of the first iteration, we find out the value of y1. The equation for y is 1 by 11, 33 minus 4x plus z. So here the x should be x1 and z should be z0. So x1 is 2.5 and z0 is 0. So if we substitute these values, we obtain y1 as 2.091. Obviously there are some digits towards the right, and I am restricting it to only 4 significant digits. So that value is inserted as the value of y in the first iteration. Now in the last step, that is the third step of the first iteration, we substitute the values of x. Here it is x1 and y1 in the relation for z. The relation for z is 1 by 12, 36 minus 6x minus 3y. x1 here is 2.5 and y1 is 2.091. By substituting these values, we obtain the value of z1 as 1.227, and that value is inserted in this cell of the table, that is the value of z in the first iteration. Now we move on to the second iteration. In the second iteration, during the first step, we calculate the value of x2. That is, we replace the value of y with y1 and z with z1, and we obtain the value of x2 as 2.977. And in the second step, for the second iteration, we find out the value of y2 by substituting the value of x as x2 and z as z1 itself. So it is 2.029. And in the third step of the second iteration, we obtain the value of z as z2, that is 1.004. Here we substitute x as x2 and y as y2. That is, whenever we are finding out the value of a particular variable, we use the latest values of the variables. And in the third step, we obtain x as 3.01, y as 1.997, z as 0.996. In the fourth iteration, we obtain x as 3, y as 2 and z as 1. Now in the fifth step, again we get x as 3, y as 2 and z as 1. Even if we repeat the iterations, the values are not going to change. So we end the procedure here and we obtain the solution for the system of equations as x equal to 3, y equal to 2 and z equal to 1. And in some cases the values of the variables won't converge to such integer values. In that case we have to end the iteration once the repetition is to the desired accuracy. And to summarize, the Gauss Seidel method can be used for solving any system of equations in which each variable can be expressed as a function of other variables. And the references are these. And that's all. Thank you.